Hi there. Let's get started with the Unit 3 review for Euclidean triangle proofs. This will be part 2, the part with the problem solving and the show your work. Again, let me refer to the links I have here on the screen. One is how to do proofs, courtesy of Wikipedia, and you can copy that link, type it into your browser, and check that out. And if any part of a proof or anything in this unit bothers you, go back to emathinstruction.com and make sure to watch the appropriate video provided online at that site. So, let's begin. In the following diagram, BD is perpendicular to AC, so I'm going to mark that with a box to indicate the right angle here, and another right angle here. It bisects angle ABC. This is ABC right here, the whole thing. So a bisector is meant to imply that it's been divided into two congruent angles. Which triangle congruence theorem would be used to show that triangle ADB, which is the upper one, is congruent to CDB, which is the lower one? Well, we have a shared side here, and when we look closely at this triangle, hopefully you can see that we have an angle-side-angle relationship. So I would pursue angle-side angles. We would show this by stating things like since BD is perpendicular to AC, both those base angles there, both angle ADB and angle CDB are right angles, and all right angles are congruent. After that, we can focus our attention on BD bisecting angle ABC. Since BD bisects angle ABC, we can conclude that angle ABD and angle CBD are congruent. This is because an angle bisector divides an angle into two congruent parts. Finally, the two triangles share a side. And this side is BD. Because it is included, it is a part of each of those two triangles. And that would be that. Continuing on with problem 14, we have a diagram here. Has a lot of letters in it, so I sort of prepared this proof beforehand, as I'll do the other ones in this review. In the diagram below, it is known that angle QUS, here it is, QUS, is congruent to angle TUR, which is right here. Again, I prepared that. So we have two angles that are the same, and I'm noticing right here in the middle, they both have a piece that is in common to both of them. And our proof thing involves proving that angle QUR, I showed that in orange, is supposed to be congruent to SUT over here, also in orange. So blue, I marked the things I know, and orange, I marked the things I want to prove. So my strategy here is, as I looked at it initially, since they both share this piece in the middle, if I could subtract it away, the remaining values would be congruent. So you could see here in the proof, I started off by saying the given information, and in step 2, I show the breakdown. In other words, I'm showing that angle QUS is actually, and here it is again, QUS is actually the sum of two smaller angles, QUR as well as RUS. In the same step, I do the same for the other angle there, which is angle TUR, so I won't color it, but the other large angle here. And that also is equivalent to adding together angle SUT, this one, and RUS. If you look carefully now at what I've written, you can see that I have two angles here that I've added on to each of those situations. Well, this is where I say now we need to move on to, first of all, let's say that angle, let's take these parts and set them equivalent. QUR plus angle RUS, this part here, is actually congruent to the other side here. Angle SUT plus angle RUS. And what I did here was some substitution. And basically what I said is, since up here this is the same thing as this in step 2, then it stands to reason that what they both equal must also be equal. So I substituted the two ideas into this one statement. In number 4, now I'm going to out and out say how angle RUS is congruent to itself, because until I do so I can't really go ahead with subtracting it, because I haven't said anything about it yet. So that would be reflexive. And for step 5, I can now say by subtraction, if I subtract this away from this, what I'm left with is that what we wanted to prove is so, that angle QUR is congruent to angle SUT, and the reason here was subtraction property. So think carefully, look this over, because I realize there are steps here that you likely would have skipped. But the strategy here is, of course, start with the given, set up showing how these parts equal those large angles, so that you can then refer to how they both have this angle RUS. We say that this is equal to this in this third step, and then we say RUS is congruent to RUS reflexively, so that when we say we're subtracting it, you can see that I've already covered my behind by saying that these two angles were the same thing. Loud and clear. And there's my QED. I realize some of you would not do the reflexive property, and you probably would be inclined to jump from step 3 to step 5, and I could see why you would do that, and I might accept that as well. Moving on now to the next problem. Problem 15 shows a diagram here with a parallel line situation. M and M are parallel, and the first thing I'm thinking about that, particularly given this diagram, is I'm thinking about alternating angles, congruent, and stuff like that. AB is congruent to AC, which I've marked over here, and the things marked in orange are the things we need to prove. All right, so I started preparing, and I have the given down here. And some things I'm thinking about is, well, if I want to prove 1 and 2 are the same thing, I'm noticing that there's a relationship when I look at the parallel lines. Let me get a different color. I'll use, I don't know, violet. Here's a transversal, and here are some parallel lines, which means that angles 2 and 4 are alternating angles, alternating interior angles, and they're always congruent. That goes the same for angle 1 and its relationship to angle 3. And so I'm thinking here, I see an isosceles triangle. I realize that base angles in isosceles triangles must be congruent. So if I say it's an isosceles triangle, I can then say that 3 and 4 are the same thing. And then I can move on to saying, since the lines are parallel, that 4 is the same as 2 and 3 is the same as 1, and go from there. So for step 2, I'm going to say that angle 2 is congruent to angle 4, and angle 1 is congruent to angle 3, and my reason here is because of alternating interior angles. Alternating interior angles formed by parallel lines are congruent. Now I can go to step 3 and go directly to saying that angle 3 must be the same thing as angle 4. Do you know why? Base angles of an isosceles triangle are congruent. You're probably wondering if you should have first taken a step to say it's an isosceles triangle. It's kind of unnecessary since the marks there indicate it's a definition. It is a right triangle. You don't really have to say it. It's sort of obvious. Now that we've said that, we can just jump right ahead. Since 3 is the same thing as 4, and we've already mentioned them up here, we can sort of swap out that idea. If 2 is the same as 4 and 1 is the same as 3, but 3 and 4 are the same, you might say transitive. I'm going to go with substitution. So angle 1 is congruent to angle 2, and I would go with substitution. QED. Short and sweet. At problem 16, you can see it's already labeled up because this one's relatively simple. You're told that HF is this line, HF is bisecting angle EHG, which again means that we have two smaller angles that are congruent here. I've already marked them. We're told that EH is congruent to HG. Again, I've marked it. And I've already marked the one side here that's shared by the two triangles. So in step 1, I go ahead and mention all these given ideas, and I just wanted to get that midline out of the way first this time, so I just said HF is congruent to HF because of the reflexive property. I went on to say that these two angles in here are both the same thing or congruent, and this is because an angle bisector divides an angle into two congruent angles. So this one is the same as this one. Okay. Having done this, I've already now covered the three parts that I need to say the two triangles are congruent. So I'm going to go ahead and say that triangle EFH is congruent to the other one, GFH. And by referring to the picture, I can see the reasoning here is my SAS theorem. You could just say SAS. I guess I'll write theorem this time since I said it. That's up to you. Now that I know the two triangles are congruent, the idea of this proof was to prove that something else entirely that we didn't use was also congruent. Specifically that this piece here is the same thing as this piece here. And so the idea behind this is that once you know that two triangles are identical, you can refer to any of their corresponding parts and also say that they're congruent. So the worst of the job is over, and I'm at my final step, and I just say that EF is congruent to GH, and my reason here is CPCTC, which stands for, again, corresponding parts of congruent triangles are congruent. And who wants to write all those words every time? So we just say CPCTC. You know that has a rhythm. For problem 17, you could see that I've redrawn this picture over here in the lower right side in orange. What I did was I took the original picture and I rotated it 90 degrees to the right so I could reorient it and better illustrate to you what you should be seeing. And you should know that any rigid motion transformation still produces a congruent image, so I haven't changed any of the dynamics of the problem. I prepared already the statements for all the given information, so I know that NM over here is congruent to OQ, and I've marked it. I also know these two lines are parallel, and this is actually why I turned it around. And I marked my right angles over here in the picture and down here as well. I used the green line to show what I'm trying to prove. So that's not given. This is the direction we're headed in. When I rotate this, you might better see how if these two lines are parallel, and let me mark them again as I'm speaking about them, as this one is parallel to this one, you might better be able to see this transversal going through it. In which case, you can say that this angle over here actually corresponds to this one. You see the cluster of four angles here? And remember how when you have that cluster, every angle corresponds to the other cluster of four down below. I extended these so you could better see it. You are allowed to do that. So, this is very helpful for me because now in step 2, I'm going to say that angle NMR is congruent to angle OQP. And my reason behind step 2 now is that corresponding angles created by parallel lines are congruent. So my focus of attention honestly is that I see this triangle here, or triangle here, MNR, and I see the other one here. And based on, they both have the same sort of markings. They both have a right angle. They both have a congruent side. And now by doing the corresponding angle comment, I can say that they also have another angle congruent. So if you look closely, I have a right triangles, but this is not hypotenuse leg because I don't have any values on the legs. But it is angle, angle, side. One angle, second angle, and the side. Congruent over here to this angle here, this second angle here, and this side. So having said this, I'm now going to go to step 3. I have to say that perpendicular lines form right angles. So I'm going to say that angle NRM and angle OPQ are right angles. And I'm sure you can guess the reason why. Perpendicular lines form right angles. Lines, segments, honestly, I guess, in this case, form right angles. Once I've said they're right angles, now I can go on and talk about how they're the same thing. So angle NRM is congruent to angle OPQ, and that's because all right angles are congruent. Finally now, I can go ahead and say how these two triangles are the same thing. So triangle NRM is congruent to the other one, triangle OPQ. And my reason for that is angle, angle, side. You could say theorem if you want to look fancy. Now that I understand the two triangles are the same thing, this is again where we come back with that CPCTC idea that any of the parts of these two congruent images also have to be congruent. So now I can say that those lines I marked in green are the same thing. So NR is congruent to OP because of CPC-TC. Ta-da! Problem 18 shows us a diagram again with parallel lines. So you can see these are really popular questions. And we have two line segments, AB, which goes left to right, and CE. They're both intersecting here at point D. And D is the midpoint of AB. So I already am marking this, and my reason behind that is definition of midpoint. Midpoint divides a line segment into congruent parts. I don't know about the other pair of lines being congruent. That's what we're supposed to be proving ultimately. When we want to prove that D is the midpoint of the other pair of sides, I want to show that these two pieces here are the same, in which case D must be the midpoint. I have vertical angles already marked because that's kind of an understood no-brainer. And another task for you to realize is because these are parallel lines, and I've extended them again so you could see them better, AB is the transversal line right here, in which case you could see that I've indicated that this angle here at B and this angle way over here at A are both alternate interior angles and they're congruent. So in step 1, I laid out the given information, and in step 2, I did mention the alternate interior angles are congruent. We can say that because it was said in the first statement that those lines connected with them are parallel. Part 3 here, I go on to say that AD is congruent to BD, again, because we were told that D is a midpoint, and that also is covered here in part 1, or step 1. I can now go say a midpoint divides a line segment into two congruent parts. So if I look closely at this image here, all I have to do now is I've covered these two angles, I've covered a side, I need to focus my attention on the vertical angles here. I've already written the reason, so I'm just going to say here that angle ADE is congruent to angle BDE because of vertical angle theorem, BDC. Having done that, I've covered an angle, a side, and an angle on each of them. So I'm going to go to it and say that triangle ADE is congruent to the other triangle, which is BDC. Now, the reason this had to be done first is because I want to talk about the parts that I labeled in green, which happen to be the corresponding parts of each of these two triangles. So I want to say that these two triangles are the same, and I have. So now I can go ahead and talk about any of their corresponding angles or sides. And in this case, it's the side I want to talk about. So I'm going to say that ED is congruent to CD, and this again is because of CPCTC, or corresponding parts of congruent triangles must be congruent. So finally, after I've said that, I can get to the proof statement, which was that D is the midpoint of EC. And I've backed it up. I've shown everything. And the reason here is simply definition of a midpoint, or that a midpoint divides a line segment into two congruent parts. QED. Problem 19, we already have a construction drawn out for us, and we just have to be able to understand what's going on. So Serena needed to bisect angle A over here, shown in the diagram. So she located points B and C, as you see here, B and C, such that AB is congruent to AC. So what that means is she put a compass on the paper. You could see her needle went here, and she drew an arc that went around like this. I'm a little off, but you know what I'm saying. So when she did that, she created something that we're two positions here that were equidistant from point A. She then located point D, which is over here, such that BD is congruent to CD. So she did the same thing. She put her compass point now on each of those points independently. So she put the compass point first here on B and opened it out to here and drew this arc. She kept the compass the same position, put the needle to C, and she drew the arc in the other direction. So by doing that, she now knows that this segment here, BD, is the same thing as DC. They're congruent. If you look at the two triangles individually, realize that they both share a side. So by the reflexive property, we can say that AD is congruent to AD. Hence, these two triangles must be the same by side, side, side. Because the two triangles are the same, and we want to talk about whether this angle does AD bisect BAC. Well, if AD was bisecting this angle here, that would imply that these two must be the same. Well, they have to be, because if two triangles are illustrated as being congruent by SSS, then their corresponding parts must also be congruent. So in answer to this question, because it's not a proof, you want to just write in words what's going on. I'm going to write it for you. Yes, AD does, ray AD, does bisect angle BAC. We know from how Serena did the construction that AB is congruent to AC. Oops. And BD is congruent to CD, as I explained already. We also know, reflexively, that AD is congruent to itself. By the reflexive property. That means that these two triangles are congruent by SSS. Since the two triangles are congruent, angle 1, this one, must be congruent to angle 2 by CPCTC. Corresponding parts of congruent triangles are congruent. This means that AD, ray AD, bisects angle BAC by definition of angle bisector. And that is an angle bisector divides an angle into two congruent angles. Problem 20, we have two triangles again, and this problem is a little difficult to explain because we have to go through two triangle congruencies. The strategy here is first to say that these two larger triangles are the same, And then we're going to focus our attention on this one here and this one here so that we could say they're the same. And finally, we'll be able to say by CPC/TC that the green lines here, or our proof statement, are the same thing. So I already started off and provided the proof for the two larger triangles. We have our givens. We can say that the two vertical angles marked in blue are congruent, in which case these two large triangles, STW and VTQ, are congruent by side angle side. Once we've got those two declared, we now need to move on to think about the smaller triangles. So my fourth step, I'm going to say that angle UST is congruent to angle RVT. Let me highlight these with a different color so you see what I'm referring to. Angle UST is this one, and I'm saying it's congruent to RVT, which is this one. And that's because we've already said the two larger triangles are the same, so I'm going to say here for step 4, corresponding parts of congruent triangles are congruent. As I look at these two smaller triangles, I've already declared these two sides the same when I did the first part. Or actually, well, it was given. I've now said that an angle is the same within these two small triangles, this purple one with this purple one. And here what I marked in red is going to give me my second angle so that I can show that this triangle and this one are the same by angle, side, angle. So step 5, let me just mention those vertical angles. Vertical angle UTS is congruent to the other one on the other side, which is VTR. Vertical angles are congruent. And step 6, I can say these two smaller triangles are the same now. So I'm going to say triangle STU is congruent to triangle VTR. My reason for that one is ASA theorem. So actually now I am at my last step. The difficulty in the problem is being able to plan and see your way through it. So I'm going to say that RT is congruent to UT by CPC/TC. Diagram with the following information provided. We know that BD is congruent to CD, so we mark it so. And we see here that we have an isosceles triangle. We're also told that BD bisects angle ABC, which means that this angle must be the same as this angle. Having said that, we can continue our thought flow. We're supposed to understand at the end of this that this triangle here, DAB, is isosceles, and we have to be able to justify that. So working around this is not a statements and reasons type of proof. They just want you to explain what you're thinking. And so what I'm thinking here is that if this is 70, this one must be 110 degrees because these two are collinear. They're sharing the same line. Therefore, linear pairs are supplemental, and that has to be 110. Moving from there, I see that this is an isosceles triangle, and I know that base angles must be congruent. If the whole triangle measures 180 degrees, and I already have 110 degrees accounted for up here, that leaves 70 degrees to be divided equally to these base angles. So they must be 35 degrees each. Since this angle ABC was bisected, as stated in the given information, this angle and this angle here both have to be 35 degrees. Keeping in mind that we want to show that this is an isosceles triangle, we can work with the idea of the whole triangle equals 180 degrees. And we already have a 70 and a 30 accounted for. I'm sorry, a 35, which totals 105 degrees. When we subtract that, sorry, yeah, that's right, 105 degrees, we find that the next angle, the resulting angle, or the third angle of this triangle must be 75 degrees. So in answer to the question, is triangle ABCD, DAB isosceles? The answer is no. Triangle DAB is not isosceles. You can either write out everything I just said in paragraph form. Certainly you could show this, but it does say justify, so you might want to put some words down. Although personally, I think that all the filling in of the information here is the justification. But it's not isosceles because the base angles are not congruent. And that's the end of that conversation. In problem 22, we're given information about a quadrilateral, and we're told that the opposite sides of this quadrilateral are congruent. So I'm going to label them as congruent, and this pair is congruent with this pair. My plan here, in order to choose to be able to say that these two lines EF and HG are parallel, is to be able to, by drawing in a transversal line between the lines, if I can show that the alternating angles, this one here and this one here, are congruent, then I know the two lines must be parallel. So my plan of attack here is to prove these two triangles, EHG and EFG, are both the same thing or are congruent, and I'm going to use SSS. So for statement 1, I go with the given information, which is stating that those two opposite sides are congruent. And that already takes care of two sides. Next, I want to discuss the line I've drawn in there, creating the transversal. And I'm going to say that it's congruent to itself because of the reflexive property. Now that I can discuss how these three sides of these two triangles are the same, I can now go ahead and say that the two triangles are identical. So I'm going to say that triangle EGF is congruent to triangle GEH, and I back that up with SSS. If the two triangles are the same, that means their corresponding parts must be the same. So that implies that the two angles that I've numbered as 1 and 2, because I'm tired of all these letters, are congruent, and that's because of CP, CTC, or corresponding parts of the two congruent triangles are also congruent. So finally, last step, I can confirm that EF is parallel to HG. The reason is because if a pair of alternate interior angles created by two lines crossed by a transversal are equal or congruent, I'll say congruent, then the lines are parallel. QED. This is our final problem. It's problem 23. And we have a strange diagram here that I've already labeled. AEC is this large angle here, and it's told to be congruent to this large one over here. We also know that ABE, this bottom one here with double lines, is congruent to this one down here, DCE, and I've marked those. And we know that AE is congruent to DE, so I have these upper pieces. The things I've marked in green are the things I hope to show are true, that they are congruent, because if I can say that, then I can say that the triangle BEC is isosceles. The way I'm going to approach this is to show that this triangle here and this one here, these two, this one and this one, are the same. And I'm going to use, I think I could use, looks like angle, angle, side. The thing is, this angle here in the middle, we've got some overlap area. So, like previous things that we've done before, hopefully you're realizing that if we subtract this central angle right here, this one, from each of these, those remaining angles will be congruent. So let's begin. I've got the given information written out, and next step I'm going to take is to say that angle AEB plus angle BEC, which is that middle one, is the same thing as angle CED plus angle BEC. So you see that I have BEC, it's part of both of these two initial larger angles. See that? And so hopefully you're seeing that if I say that BEC is the same thing, this is a questionable step, but maybe you want to say that BEC is congruent to BEC, then I can subtract it and the remaining information should be congruent. The reason for 2 is you see I'm adding parts together. That's the whole is equal to the sum of the parts. Okay. You can't really go with addition until you say that if you said this first, maybe you could, because then you could say, no, you can't, because we don't even know that these two are equivalent statements at this point. Number 3, though, when we bring in reflexive, the idea is not that we're adding the two parts to find out the large one. The idea here is we want to get these small ones. I'll mark them in a different color. And be able to say that if this one is the same as this one, we have two congruent angles in both these triangles. So we have to subtract out this middle portion. I hope you're seeing that. So in step 4, let's use the subtraction property. And I'm not going to show it, I'm going to jump to it. If I can subtract this and this because they're both the same, I'm left with that angle AEB is congruent to angle CED, which are those two red ones that I was trying to show were the same thing. And the reason is subtraction property. Next, I can now say those two triangles are the same. So I'm going to say the triangle ABE is congruent to triangle DCE. And my supporting theorem is AAS. Finally, I'll get to the point here, those green lines, I can say that BE is the same or congruent to CE. And we use that ever popular CPCTC. Therefore, final statement is our proof statement. Triangle BEC is isosceles. And basically the reason is definition of isosceles triangle. And that's the end of our review. I hope this helps you out. Again, backtrack, slow it down. I can't spell. And watch the parts that are most important to you or the parts you're really not getting so that you can sort of dream on that a little bit and lock it into your brains. Hope you do really well in the next test. I know this is a tough topic. Hopefully, the rest of the year will be a little easier. It's less abstract. Thank you.